Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I guess I'll start. So my name is Robert Veronesi. In fact, I got a little slide introducing myself. I got my PhD at the Free University of Amsterdam under Andy Tannenbaum, working with people like Guido van Rossum, who did the Python language for the Amoeba distributed operating system that I was building at the time. And then I worked at AT&T Research, Bell Labs in Murray Hill with Plan 9 people. And since '91, I've been at Cornell University, where I first the pleasure of meeting Lorenzo. There I worked on a system called Horus that was licensed to Stratus. I co-founded something called Doglobs, which was acquired by something called Fast, which then was acquired by something called Microsoft, which some people in the room here have heard of, which is a search engine company. And that was together with my colleague Fred Snyder. We did something called chain replication for Fast, and also leader election protocol that I believe is in use today in Microsoft products. Then I did Reliable Network Solutions. That was a company with my colleagues Werner Vogels and Ken Berman. And Werner Vogels, of course, is now CTO at Amazon. We did developed gossip-based solutions there, and some gossip I'll be talking about in these talks. And then I also worked a bit for the database company Greenplum, which was acquired by EMC. So that's my background, and let's talk a little bit. Wait a minute, are these the same slides? Uh-oh, it's not the right slide. Let me see, I may have the wrong slides set up. Huh, what happened here? Let's see. This is an old version of my slides. So hopefully the new version is here. Hopefully my PowerPoint works. Come on. There we go. Hopefully these are the new slides, otherwise I'll just be working with the old ones. I edited them this morning, so should know. That's weird, huh? Okay, well, maybe that's just the way it is going to be. Okay, well, sorry about that. I was going to ask you guys about why processes communicate, and I don't know what happened to those slides. But here, the answer's already. But let's just talk about this a little bit. Before we talk about distributed systems and communication, it's kind of interesting to know why processes communicate. So, seems pretty obvious why processes communicate. But when you really go and take a step back and you look at a lot of these algorithms, the reason they communicate really is because they want to share some part of their state with other processes. It's basically a poor man's substitute for shared memory. They're not sharing memory in a network system, and so the only way they can impart some of what they know is by sending a message to the other processes. I mean, I have here some other examples. I mean, clearly, when you take your web browser to a website, the idea of communication is simply to copy bits. There's some stuff that's stored at the web server and that you somehow want to have at the web browser. That's done with a message. But that's also an instantiation of the web browser wanting to share some state with the browser. sometimes you actually want to transfer the bits. The source doesn't really care about them anymore, but there's some destination that cares about them. Email is a good example. Send email from one place to another. But again, like really the source and the destination are trying to share some state. Like when I send an email to Lorenzo, it's because I want to share some state with Lorenzo. So again, it's a substitution for shared memory. And so really, the reason that one process sends a message to another process is to impart some information that it has. So what kind of ways are there to communicate? Shared memory and message passing. And they have their advantages and disadvantages. Shared memory is of course a very convenient abstraction to have, but there are a lot of we already talked this morning about locks. There are some other ways for processes that share memory to synchronize with one another. It tends to be hard to implement in a truly distributed system where there's lots of machines that are connected by a network. Can be done, but we have not really been able to scale that solution. So message passing is really all we're left with, based, where messages are being sent and delivered. But it's as we can see from experience, fairly error-prone way of doing things. The message passing API itself is fairly simple. This is what we'll be working with. There's a down call to send a message to a particular destination, and then there's an up call that's delivered at the destination that specifies the message and where it came from. So, but what are the semantics of send and deliver? Because it's not necessarily all that clear in a distributed system what one will get out of this. I mean, for TCP, for example, it's, when you send a message, is it really guaranteed to be delivered? Well, only under certain assumptions, because TCP connections can break if it takes too long. And so let's see what we want. So before we do that, before we can talk about the semantics, we have to talk about what processes that send and receive messages, how they may fail. So they, let's do this. Bigger letters, good. Now I can read it too. So processes can crash, which means that a process processes make transitions. They have some kind of specification from which they work. They have, state, things happen, timers go off, messages are received, and based on that, processes make transitions until a process crashes, in which case, process makes no more transitions. So that's, sometimes called a benign failure, a non-Byzantine failure. It's just process stopping for whatever that reason that is. Maybe the power disappears or something like that. We're going to define a correct process to be a process that never crashes. It's kind of a weird thing, a weird concept. You think of it. So, because we're going to consider a process that is going to crash faulty. However, how do we know that a process is going to crash? Well, we don't. But we're nonetheless going to call it that faulty, and as we'll see in a minute, that has some advantages. We're also going to assume that these crashes can be detected somehow and accurately. Of course, you can try to ping a process, and that way you can suspect a process being faulty. But as we'll see in a bit, under the asynchrony assumption, which is really a lack of assumption about timing, you can be sure that a process is crashed just by pinging. Nonetheless, we're going to assume that we can accurately detect a crash. And in particular, a correct process is never considered faulty, and a faulty process is eventually detected and reported. Not necessarily at the same time, though. Okay, so here are the semantics of the send and deliver primitives that we want. So first of all, we want if a correct process P invokes a send primitive, wants to send a message to Q. And P and Q are both correct, which means they never crash, ever. Then eventually the process Q will deliver that message and invoke this opcall, deliver PM. That's a liveness property. Something good eventually happens. That's a very good example of a liveness property, I think. And here's a very good example of a safety property. It says if some process Q, and I don't care whether it's correct or faulty, delivers a message from P, well, then it had better be the case that P send that message. So there are no messages delivered out of the blue. If that were to happen, that would be bad. And that's why this is a safety property. This says, like if you send a message, eventually something has to happen as a result. That's a liveness property. Now we're going to consider all these messages to be unique. And why is that? Well, think about it when, say that different processes could send the same message to Q. What does that really mean now? Like the process may deliver, well, actually, it's not so much when it's different process sending to Q. Let me see. When the same process P sends multiple messages to Q, these particular definitions get a little murky about invocation. It might be that some of those messages got lost, some of them didn't get lost. If you send a message 3 times to Q, should it be delivered 3 times? Just to get away from all that murkiness, we're going to just consider every message to be unique. Okay, so when you cannot send the same message twice, the process will not send the same message twice. So now it should be clear, although it probably is not yet, but we're going to make it clear why we define a correct process the way we did. Like we said, a correct process is one that never crashes. And a faulty process is a process that is not correct. So somebody maybe say why that is. Say that wasn't the case, that the process is only faulty after it crashes. At the time that it crashes, it becomes faulty. I mean, if that were the case, then faulty processes could not possibly invoke send, right? Because a crash process is one that doesn't make any transitions. And so these definitions really don't mean much anymore if a process is only faulty after it has crashed. So it would mean that if a correct process invokes send, then it has to be delivered, even if it crashes right at after invoking send. It would be very hard to implement, for one thing. Definition wouldn't make much sense. The implementation would be very hard. That's why it's easier to just consider a process that never crashes correct and a process that at some point might crash faulty, even though clearly we cannot tell the future, but it's the easier way to think about these failures. That way we can also put bounds on the number of processes that may crash, the number of faulty processes, and that makes a lot more sense too. Yes?
Why not define that liveness condition slightly differently? And instead of making assumptions about whether a process is correct or faulty, just say that if a process, if a deliver is encountered, then the messages are eventually sent to all of the correct processes.
Sorry, if a deliver is encountered?
If the system delivers a message, then that message is eventually delivered to all other processes, all of the correct processes. But this could happen on a correct process or a faulty process.
Well, I mean, so the safety condition here is that if a deliver upcall is invoked, that it's only to P. I mean, we're not talking about broadcast here, right? So the point-to-point communication primitives where a message is sent to a particular process. So when it's delivered, we do have the guarantee that it was sent by some process. I don't know what you mean by...
But it is also delivered to Q.
Also delivered to Q. I'm not following, sorry.
So I was talking about the liveness.
Oh, the liveness.
Yes. Instead of defining liveness for correct processes only, is there some way we can define liveness even for a process?
For faulty processes?
For faulty processes.
I think he means if you generalize it to say if you send, he sends Q,
Mm-hmm.
if it gets a confirmation, and then it's given the guarantee that it will be able to be delivered. So you have to add one more event, I guess.
If you add like an acknowledgement event or something like that. Yeah, I don't know. The primitives here are simple one-way message sending, and so there's a process that sends a message, another process that delivers the message. And it doesn't really make sense to think about what it would mean, what the semantics are of a faulty process sending a message. That faulty process may have crashed just before sending or just after sending, so it may or may not be delivered. And that's in fact captured here. It doesn't say that if a faulty process crashes, that a message that it sent cannot be delivered. It's a faulty process, a message from a faulty process may be delivered, in which case we know that the faulty process sent it. But it doesn't guarantee that if a faulty process invokes a send primitive, that it will eventually be delivered, since those are just the semantics as defined under this failure model.
What's the guarantee for messages for which a faulty process receives a deliver?
The only guarantee that applies here, I think, is this one. If a faulty process delivers a message, it was sent by some process. We don't know whether that speaker up here. We don't know whether the process that sent the message is faulty or correct, but that's the only guarantee that applies, because that particular guarantee only applies to correct processes. Okay, I think I should probably move on, but I'm happy to discuss this further offline. So how's it implemented? It's very simple, really. In order to implement these particular semantics, you just have to keep on retransmitting until either you receive an acknowledgement or until you find out that the destination has crashed. And again, we're assuming that we have a reliable notification mechanism. So that's pretty easy. There are implicit assumptions underneath here that that were actually brought up this morning. We do need to assume that the link between P and Q is fair. That eventually some messages will get through. If we're not assuming that, and none of these replicas of the messages that are sent are ever delivered, this would still not work. So there's an implicit assumption here that the link is fair. And then so as soon as you receive one of these messages, you deliver it only the first time. You want to filter out duplicates, and every time you receive a message, you send back an acknowledgement, and that will do the trick. It's a protocol that, in fact, is quiescent. Will eventually terminate once the message is not only when the message is reliably delivered, but when the sender has detected through the acknowledgement that it has been delivered. It will stop. Eventually, this protocol terminates. Again, under the assumption that failure detection is accurate and links are fair. So it might make sense to stop here for a second and figure out what if the failure notification was not reliable? What if we didn't have an accurate failure detection service, and so we would never know for sure that Q was faulty or not? Would this protocol still stop? Would it still terminate? Any clues? There's only two answers.
I guess not a way, because you keep on retransmitting and there's no end in sight.
Right. You would never ever know, if you don't get an acknowledgement, you don't know whether the process queue is faulty, or whether every message you sent so far got lost, or maybe they all got there but all the acknowledgements got lost, or in any case there's never been a correct delivery and a correct acknowledgement coming back. So you would never be able to stop until you receive an acknowledgement. And of course, if queue is in fact faulty, you would receive that acknowledgement, and so this protocol would not terminate. So timing, heard a lot about timing this morning. So we're going to make no assumptions about timing. We're going to no assumptions about the delay of messages, no assumptions about the time that it takes to process a message once it's delivered. No assumption about how long it takes for failure to be notified after it happens. No assumption about clocks. So the clocks may be running arbitrarily fast or slow. They may be skew between the different processes. You know, one process may think it's 1 o'clock in the afternoon. The other one may think that it's in the middle of the night, like I do at the moment. And so it can be arbitrarily off. So we're not going to be measuring time at all. It's going to have basically make no sense whatsoever in our system, and that's what asynchrony is. You know, they're basically a complete absence of assumptions about time, and which should not be confused with non-blocking. That's also often, you know, people could talk about asynchronous, you know, RPC and asynchronous this and asynchronous that. That's not what asynchronous is. That's non-blocking. Asynchrony really, you know, in distributed systems means there's no real time, and so yeah, it's a complete absence of assumptions. So if you're not making assumptions about anything, it's very hard to do anything, right? If you made, you know, started with a system that you make absolutely no assumptions about, how would you build something on top of that? Start out with very weak assumptions, like you're trying to solve consensus in a system where we make absolutely no assumptions about anything. Well, that would be hard. I mean, that actually is kind of what the Americans would say, duh. It's clearly not, you know, if you make no assumptions whatsoever, there's nothing you can do. But we're going to make no assumptions just about time. So that's very weak assumption. On the other hand, we make this very strong assumption about failure detection, that we can accurately detect it somehow. And that actually is, you know, really the secret ingredient in a lot of what I'm going to be talking about, at least in the first 2 hours today. So why asynchrony? Well, it's kind of hard to make any assumptions that are any stronger than asynchrony in a system that we have today, right? If you send a message, if I send an email to one of you, I cannot tell you how long it will take before it's delivered. It may, you know, typically take only a second, but, you know, occasionally will take a little longer. You know, maybe some server is down, maybe some link is crashed, maybe there's been a power outage somewhere. There's no bound you can come up with. It can be arbitrarily long. You know, if you give me a bound, I can probably come up with some really bizarre scenarios that will take even longer than that. So that's one reason. Another reason is that if you're going to say, like, well, okay, let's come up with a bound. Let's say, well, you know, a message, you know, it's very unlikely an email won't be delivered within, say, a month. So now we have got rid of the asynchrony assumption and saying everything will happen within a month. Now I'm going to build a system on top of that that's going to take that month-long bound into account somehow, and you can kind of see that any algorithm that's going to wait a month for something to happen, that's to make sure that the message didn't get through before it detects a failure or something, and you know, for example, in primary backup, elect a new primary would be impossibly slow. So if you're going to make worst-case assumptions, the higher you set those bounds, the slower your system will be. In fact, if you look at some of the early attempts at building real-time like flight control systems, they failed because those bounds were just too long. And third, it's, as I pointed out, it certainly makes it a lot harder. I mean, if we had synchrony, it would be a lot simpler to come up with a lot of these algorithms. So just to make it a more fun puzzle, but also I think a more realistic puzzle, we will assume asynchrony. And another slide that I inserted here, which I guess I'll go over. So other way. So the other assumptions you can make are synchrony. So synchrony typically is defined as there is a known bound on every operation. Like there's a known bound on message latencies, no bound on how long it takes to process a message. That's a very strong assumption. It means like your system is real time. It has hard bounds on everything that happens. And then in between there is something called semi-synchronous. And there are various definitions for that, but a common definition would be that there exists bounds on all these things, but we don't know what those bounds are. And so that gives sort of a range of environments in which we can try to solve various problems like consensus. So it turns out that, for example, consensus can be solved in a semi-synchronous environment where we don't know what the bound is, but we just know that there is a bound. But for example, accurate failure detection, which requires this pinging, would not be possible in a semi-synchronous environment. We actually need to know what those bounds are. So depending on what assumptions you make, some problems become, harder, some stay impossible, some, So clearly weaker assumptions means harder solutions. And some problems are impossible if your assumptions are too weak, and it's different for different kinds of problems. So that makes distributed systems a very fun area to work in. This we kind of covered already this morning. In the absence of time, we can still talk about the order of events, and that's important. So events in a process are naturally ordered. Basically, the transitions that the process makes are. We basically assume that processes are single-threaded for simplicity. Also assume that a message is delivered after, or a message is sent before it's delivered. That seems to make sense for most people, though. In an interesting, fun little anecdote, when I was working with the formal methods group in our department, I gave them some algorithm, and they were trying to prove it correct, and they couldn't get the proof to go through. At some point, they said, "Oh, but you're assuming that a message is delivered after it was sent." I said, "Well, yeah." So they stuck it into their set of assumptions, and voila, the proof went through. And similarly, a process crashes before it can be reported. That's the accurate failure assumption. So that's also an ordering. And then the transitive closure of those things. If X happens before Y and Y happens before Z, then X happens before Z. So that's called the happens before ordering, sometimes called causal order. And if neither X happens before Y, nor Y happens before X, then we're going to say that X and Y are concurrent. So we can talk about ordering of events. We cannot talk about the time at which these events happen. So that all sounds good. But we live in a real world. And in a real world, we cannot detect failures. Like the accurate failure detection that I'm making is very hard to implement, right? As I said, you can try and do it with pinging. If I don't get a response to my ping message, I don't know anything. If I get a response to my ping message, all I know is that the process was alive and well since the time that I sent the ping. But if I don't get a response to my ping, then I don't know whether it's faulty, whether the network is broken, whether it's slow, anything can be going on. Messages get lost, crashes can happen anytime, machines can get slow. Even with accurate failure detection, some processes may have detected the failure, some other processes may not have detected the failure. So it's a very messy world out there, and so this is where the notion of virtual synchronous group communication comes into the picture. So virtual synchronous group communication was something that I think a term coined by my colleague Ken Berman at Cornell University in the mid-'80s. A lot of people, I think, have it's an interesting environment. I don't think there's a good formal definition for exactly what it means. I'm not going to give you a formal definition today, but I'm going to give you what I think it means and why it makes things simpler. And the first bullet here is really what it's about. That is, we're going to simulate an environment in which processes do not crash and messages do not get lost. Or in other words, a process in which failures do not happen. And it's going to make processes believe that all failures are gone. And then once in a while, processes do crash. We're going to reconfigure the system. And we're going to agree on a new state and continue again. So we're sort of going to divide the execution up into epochs. And then we add to that some nice tools to simplify the programming of distributed algorithms with things like leader election and broadcast protocols and all that. So how do we do that? So first, there's 4 ingredients that I'm going to go over. One important ingredient is the notion of a view. A view is just a membership, set of processes. And here's the important part about these views. There is one single sequence of views. So you start out with an initial view v0, and you run for a while, and then if some process crashes or some other processes want to join, we're going to add a new view v1, and then v2, etc., and so on. But it's a single sequence, and that actually turns out to be a non-trivial property of virtual synchrony. In fact, it requires solving consensus to get a single view, because every time you create a new view, there can be, in fact, multiple proposals for a new view. There can be only one next view after v0. There can be only one next view after v1. So, but we'll talk about that in more detail later. Then we got these epochs, which are the executions between 2 consecutive views. So the first epoch would be between v0 and v1. The second epoch between v1 and v2. And in an epoch, a process first gets a new view upcall. There's a new upcall, new view. It says what the view is. And so every process in that epoch gets that view, at least as far as we can simulate it. Right? So that happens. And again, processes in an epoch do not crash. A process in view V only knows about the process in view V. It cannot send to processes outside of V. So, and it can only deliver messages from process in V. So all it knows is that membership, that view. Until the end of the epoch, when there's a view change. There's a three-way handshake for that, in fact. So a process in a particular epoch receives an upcall, stop view or stop epoch or something like that, in which it has to acknowledge that with a down call. It says, okay, I'm done. All processes are expected to invoke that after getting this upcall. And then sometime later, it will hear about the new view, which starts the new epoch. So that's the handshake. Process comes, is busily working in some view, gets some upcall, stop view, then it yields. After it yields, it's no longer allowed to send messages until it hears about the new view with the new membership, and then it can start sending messages again. So And we're going to get rid of faulty P because we're simulating an environment in which failures do not occur. So the only thing that do occur is these view messages. But that's at the end of the epoch. So during the epoch, there are no failures. At the very end of the epoch, we get a new view notification.
So processes really never die.
Processes never die.
Right in the sunset.
They are off in this epoch. They just send messages. They deliver messages. We're simulating an environment in which they don't die. I mean, we may no longer hear from a particular process, but as far as our simulation is concerned, it is still alive. It's just no longer sending messages. So yeah, there are no failures. And so if a process is in some view and it's not in the next view, that really means that as far as we have been able to determine, it has crashed. And in fact, we're going to assume that failure detection is still accurate, so in fact it has crashed. Yes?
So if a process does crash, then would the system guarantee that if P is in V, it will not be in V? Or
yes, that is what we're going to guarantee that. Because we're assuming that failure detection is in fact accurate, the underlying implementation is not going to remove a process from a view, or from a, it's going to keep that in the next view unless it's really faulty. So processes, so P being in V but not in the subsequent V prime means it's really crashed. It's dead. It's gone.
My
Yes.
question was that if a process crashes during an epoch, are you guaranteed that it will not be in V prime in the next epoch, or does it not matter?
Yeah, I mean, so we have to make a difference between the abstraction and the implementation of that abstraction. So in the abstraction, processes don't crash. In the implementation of the abstraction, processes, of course, do crash. And we're going to guarantee that if that's the case, so that it's crashing during the epoch, it will not be in the next view. It will not be in the next epoch.
But even if it is in the next epoch, then for the abstraction, it should not matter.
It does because of the following property, the last ingredient, which is there's messages don't get lost in an epoch. And so all the messages that a process sent also have to be delivered. So if P sends a message to Q, and P and Q are both in the original view and in the next view, then clearly those messages have to be delivered. But we're going to go a little further by also saying that all the messages that were sent prior to M, according to this happens before relation that we defined, have to be delivered in that view as well. Like, messages cannot get lost. And that means that, if some message is delivered, then all prior messages better had to be delivered as well, or clearly there would be a way to detect that there are failures. Lorenzo.
So when you say that messages cannot get lost, is it okay for, do you have the situation of a tree that is falling in a forest and nobody hearing then?
It's just an abstraction, right? So, yes, so if we can hide that from the other processes, then we're fine. So yes, it's like the tree in the forest. If nobody else has noticed that a faulty process has sent a message and then it crashes, there's actually no obligation on our part to deliver that message.
So if a message is seen by a correct process, then you're providing the guarantees that all the messages
Then right, if that message is delivered to a correct process, then all prior messages better have be delivered as well. Otherwise, somebody can detect that we're not implementing the abstraction correctly. Let's see. So yes, we're not actually. Let's see. What is this? Okay, so we cannot deliver a new view until all processes have yielded the old epoch. So. So yes, so views can only be instantiated once all correct processes in the previous view are okay with that. Yes.
And the B and B prime is to ensure that you have delivered only processes that are alive, right?
Yeah. Right, so the intersection between V and V prime are in some sense the processes. Well, all processes in the abstraction are correct until the end of the epoch, but then at the beginning of the next epoch, we're allowed to remove some of those old processes, and those will be the processes that have crashed. But we can replace some of them with new processes, so we're allowed to add new processes. And so this is in many ways an elastic type of primitive where we can change the membership over time. Lorenzo.
I just wanted to point out that you have drawn basically a very strong connection between leaving an epoch and being crashed.
Yes.
Processes may elect to leave an epoch even if they're not crashed.
Yeah, that's correct. I mean, so processes may elect to leave an epoch and just say, okay, I don't want to have anything to do with this anymore. As far as the other processes are concerned, that process crashed at the end of the epoch. What I'm not going to allow is a process that's taken out of a view that hasn't yielded the old view to go on and live its separate life without having, it has to crash. If a process either has to yield or it has to crash before a new view can be installed. Of course, in this historical node in ISIS, that was not the case. A process could go on, a new view could be installed just because a process was suspected of being faulty, and that leads to a lot of semantic problems. So that's why I simplified live a little bit here and assuming accurate failure detection. Okay, so here's an example of the reliable messaging. So we got two messages here, the red one and the black one. The black one is being delivered to the third process. So, something I did in my new slide set, which hasn't made it into this old slide set because time is ordered and all that kind of horrible stuff, is that these things were nicely labeled. But so we have two views here, a view with three processes and a new view here with two processes because one of the processes crashed. One second. And there are two messages. This message here that's delivered, and that red message that was sent to another process. That process was not delivered yet, but because of the virtual singly property, there's an obligation on us to deliver that message. We have to deliver it because it's causally prior to this message. If we didn't deliver that message, these processes would actually be able to figure out possibly that something bad occurred because the fact that that message was sent, the red message was sent, may be piggybacked on top of the black message. Yes, your question.
We see that epoch and views are kind of similar because whenever an epoch ends, it's because the process crashed or something. Then it leads to a new view which comes into picture. So are they kind of similar things, epoch and views?
Yeah, I mean, and I apologize. Epochs and views, I try to make, so view is the way I define it, just a membership, a set of processes. And the epoch is the execution of those processes that happens after the view. But the group communication terminology is such that we actually don't usually use the term epoch. We call them both views. For educational purposes, I introduced a new term, but I'm unfortunately not very consistent with using it. And you don't have to be either. I mean, it's very common for people to say, like a process in view, V, executed so-and-so. And, that makes sense enough. This epoch is really defined by the view that the processes are in. Does that answer your question? This is very interesting. This is well. Let's go over this slide. This was actually one that I took out and replaced by another one, but it's good that it's here. So here's a more detailed picture of what goes on. So we've got three processes, P, Q, and R, and they're in a view together. And so P actually crashes very early on, even before it learns about the view PQR. But Q and R learn about this. At some point, they learn about that the view is being discontinued. Then they have to yield. And then at some point they learn about a new view consisting of this Q and R. So here's a message that's sent in view V. It can actually be delivered even after the view is yielded, but it's guaranteed that this message will be delivered before the new view. And so you can see that the epochs don't completely match up with one another, and they don't have to. Time doesn't mean anything in this picture. I mean, this is, for us as observers, a picture of time going down and messages going across, but that's just the way for us to think about it. What the processes see are these up calls and down calls. They don't know anything about times, but they do know about ordering of events. So the result of all this is that processes survive until the end of the epoch. That the processes that do survive in the end of the epoch cannot tell the difference between what they saw, like all the up calls, and one in an epoch in which no failures actually occurred. You could come up with an execution that's like a correct execution, as far as they know, and that's what happened, and that's exactly what we try to accomplish. And as we'll see, that makes the implementation of a lot of distributed algorithms similar. It's a little bit similar to this notion of a consistent cut that we heard about this morning. Again, a consistent cut, the cut that you see is a state that could have happened. Like it is, it could be a real thing. Probably wasn't. I mean, probably never happened. The cut that you saw didn't happen, wasn't taken at any particular time, but it could have been. We cannot tell the difference. Here again, like we're building a simulation, and that it looks as if no failure, or it could have been that no failures occurred. The processes cannot tell the difference. And so in each epoch there are no failures, no messages get lost, no processes fail. And then of course a lot of things suddenly become very simple. Let me give you some idea of that. Leader election, it becomes very simple. When you hear about a new view, the leader, simply the process with the minimum identifier, done. Leader election. There's really nothing more you need to do. I mean, and if at some point the leader crashes, new view gets installed, we take the minimum and we have a new leader. So guarantees, since there can be only one view at a time, there can be only one leader at a time. Yes?
So can I think about it this way, that even if the process crashes in the middle of an epoch, the abstraction is as though it crashes.
The abstraction is as though it crashed at the very end of the epoch. It just was slow until the end of the epoch. It wasn't making any more transitions, and then it crashed. But during the epoch, it was alive and well. And any messages that it sent, as far as we know, got delivered, and anything that happened before it. So yeah. So why is it that there's only? It's actually not completely obvious why there's only one leader at a time. Why is there only one leader at a time? Yes. Simplifies consistency, but why does this algorithm this very simple one-line algorithm here, why does it guarantee one single leader at a time? There can be only one minimum in a view, but there was another view before this, and there will be another view after that, and each of these views picks the minimum process to be the leader, and yet I'm claiming there's only at a time one leader. So why is that?
While the view is changing, we are not actually performing any computation because we are not sending the message after each. So it doesn't matter. So at one time when we are performing computation, we actually have only one leader because the view is consistent.
Yeah, I mean I agree with that. I mean that says that each view has one leader. But I'm saying something stronger. I'm saying at a time, and of course time, processes cannot tell time, but I as an observer can tell time. I can look at the execution, and yet I claim that there can be only one leader at a time. And
views are consistent, and if they are not consistent, that means that's an epoch. And then at that time, they won't actually send any message. So
this is,
doesn't matter if the leader is not same across.
yeah. Well, I don't disagree with what you said, but the answer I was looking for is that a new view cannot start until all processes in the old view have either yielded or crashed. And so if some process was the leader in the previous view, either it yielded and then it may be re-elected here as the new leader, but it still means there's only one leader at a time. Or if this is a different leader, we know that the other process must have crashed. You cannot move into the new view until it has crashed. So this very simple one-line algorithm does in fact give you one leader at a time, and it's not completely obvious. I mean, it seems obvious, but you still need to do a little bit of reasoning about it.
Still assuming accurate failure detection.
Still assuming accurate failure detection. I mean, so later, so in my talk, at least in my talk about atomic broadcast and group communication, I will be assuming accurate failure detection throughout, because as soon as you drop that assumption, you suddenly have opened up a can of worms, and you have to get into all this Paxos stuff and consensus and all that. And I was told by a reliable source that there will be other speakers that will be going into that. Chandu.
Just to check my understanding, the way I understood this is that you cannot have two overlapping views because of the yield and fade property.
Yes.
But earlier on, about 5 seconds before the slide, you posed this as a hard problem where they could have multiple views going, which is what I was confused about. There cannot be multiple views.
There cannot be multiple views. Sorry, I'm going the wrong way. So, this is this one the one you talk about?
No, same at the beginning of the slide, after you posed the problem, you said you were making a much stronger requirement. How do I know that at any given real time? No, go forward. I don't want to make you go forward. Keep going forward.
You say stop.
Keep going.
This is how far I got.
Yeah. At the beginning of the slide, you said this is a harder statement. You're making a much more stronger statement by saying there is only one leader at any given real time.
Yes.
And you got us slightly worried when you said there were multiple views that could be going on at the same time. But
if I said that, I
okay.
unintentionally confused you. So that it really is the case that when a new view is when any process learns about a new view, all processes in the old view have either crashed or they have yielded the view. So there can be only one view at a time.
Yeah, and therefore only one leader.
And therefore only one leader at a time.
So when you say that a new leader can be elected only when the previous leader has crashed?
No, there may be a new view here which includes the same leader, the same process. It may not be the leader crashed, but some other process crashed. And then we install a new view. And then, it could be that it replaces actually the old leader because it has a smaller identifier. But it could be you could end up with the same leader.
Is it? I mean, I don't.
Go ahead.
Is it okay to say that you said that at any point in time there is one leader?
Yes.
Would it be okay to say that at any point in time there is at most one leader?
That would be probably
there is no leader?
Well, it depends. In real time, it's a slightly complicated question because it has to do with the details of the view change.
Okay.
Like every view has exactly one leader by this particular rule. The leader is the minimum process of the view, and after all, epoch starts with the view and ends with the view. So there's an atomic transition from one epoch to the next. So there's exactly one leader at a time.
You're perfectly happy to have somebody to be a leader
who's
at
crashed.
a certain point in time who's crashed.
Who's crashed in the underlying thing. But the abstraction is that the process is still leader. The process doesn't crash until the end of the view. So in the abstraction, there's one leader, even though it might have crashed over here. It's still the leader, and as far as we know, it's still alive and doing stuff. That's the abstraction we provide. So there's exactly one leader, not at most one. Yes?
So the membership is fixed, the number of processes are fixed.
Every view has a fixed, every view is static.
And everyone is having unique IDs, right?
Every view is just numbered, 0, 1, 2, 3.
That, leader will be the minimum of that ID. It's very trivial that leader will be the minimum of ID because when both the things are fixed.
Sorry, I'm not hearing well.
Then it becomes a trivial.
It is trivial, yeah. It's a one-line algorithm. Yes, it's not even an algorithm, right? Because it's just the static property of every view. Any deterministic rule you apply to the view will work. I mean, there's some hidden assumptions here. We're assuming that the process identifiers are ordered some way. But when you work with these formal methods people, they get into the nitty-gritty of everything, and I tend to not go into that, but yes. Reliable broadcast. So here's the specification of reliable broadcast. Reliable broadcast is a simple primitive which some process broadcasts, and all processes, like in this case in a view, deliver that message. So here's the more formal definition. The sender is correct, and some correct process delivers M. Then all correct processes must deliver M. That's the aliveness part of broadcast. The safety part is the same as before. You cannot deliver a message unless it was sent. So that's the spec. So how could one go about that in this particular abstraction of virtual synchrony? Any suggestions for a nice algorithm? You send the message and you wait for all processes to acknowledge. Does that guarantee that all correct processes deliver it? Because, actually, so this is, again, I think a problem with, there's actually another property which seems to be missing. Sorry, this is because my slide changed. There's another very important property that's missing, which is not the safety property. It's another. It's the relay property. It says if some correct process delivers M, then all correct processes have to deliver M. That's a very important property that needs to be on here as well. So sorry about that. So this is the simple property to get, because actually the virtual synchrony property already gives you that. If a correct process sends a message, all correct processes will deliver it. But the other one is the hard one. Is it part of it?
With the OR. And typically one step.
Oh yeah. Sorry. See, I was surprised. Okay, here I had it as two separate properties on the other slide, but here it's in one property. If some correct process delivers M, then all correct processes must deliver M, and your algorithm won't work for that in that particular algorithm if the sender is faulty. If the sender, for example, only sends the message to a few other processes, it can wait for acknowledgement. But if it's crashed,
it has to send to all processes in that view.
Right, but so if the sender is correct or some correct process delivers M, then all correct processes must deliver M. And it's the second part, the OR part. If some process delivers M in the view, all processes have to deliver it. How do I implement that with virtual synchrony? It's a little hairier than it looks.
Every time you receive a message, you also send it again.
That's right. So every time you receive a message, you have to echo it to everybody else. So here's the algorithm. When you want a process P that wants to reliably broadcast a message, sends it to all the processes in V, and then whenever you deliver, a process delivers one of these messages, if it hasn't delivered it yet, it delivers it, and then it echoes it to everybody else. So why does that work? Oh yeah, sorry, I'm not keeping track of time. I hope one of you guys do. Time is up, huh? Okay, over the break, figure out why this algorithm works.